Aromaticity is essentially a special level of conjugation. To be aromatic, the molecule has to be conjugated, but a conjugated molecule is not necessarily aromatic. Let's go over the 3 rules that must be met for a molecule to be aromatic. To be aromatic, the compound must have a closed conjugated loop. This is a ring where all the atoms involved in the ring are conjugated. The molecule must also be flat. The way I learned it, the molecule was usually flat unless it was explicitly shown not to be. Thirdly, the molecule must follow Huckel's rule, meaning 4n plus 2 electrons are involved in conjugation, where n is an integer. Basically, 4n plus 2 just gives you the potential options for the number of electrons involved in that conjugated loop, delocalized in that conjugated loop. This means we can have 2, 6, 10, 14, 18, and so on, following that pattern, many conjugated pi electrons for the molecule to be aromatic. The reason we get this sequence is because 2 we get from 4n plus 2 when n equals 0, 6 is when n equals 1, 10 is when n equals 2, and so on. If the number of conjugated pi electrons that's delocalized within that loop does not fall somewhere in this sequence, the molecule is not aromatic. There are 3 classes of molecules. First, we have non-aromatic molecules, we have anti-aromatic molecules, and then we actually have aromatic molecules. In non-aromatic molecules, one of the first 2 conditions are not met, regardless of whether the third is met at all. In anti-aromatic molecules, the first 2 conditions are met, but the condition regarding Huckel's rule is not satisfied. And of course, for aromatic compounds, all 3 conditions are met. The first molecule, a benzene ring, is the classic example of aromaticity. Let's go through all the 3 checks or rules to make sure that it is actually aromatic. First, we have a loop of carbons, and they are all sp2 hybridized because of the alternating single and double bond pattern. Each carbon has a double bond, a single bond, and a single bond with an implicit hydrogen. An important thing to do with this, if you need to, is draw out all the lone pairs and implicit hydrogens as necessary. So we can go ahead and add those implicit hydrogens just to make sure. So we have our closed loop of carbons, and they're all sp2 hybridized. We can also make sure that this molecule is flat, or we can assume it because nothing is telling us that it's not. Third, there are no lone pairs that we have to consider, so we need to only count pi bonds in order to determine the number of pi electrons that are delocalized throughout this conjugated loop. There are 3 pi bonds in this molecule, which means that we have 6 pi electrons that are delocalized throughout this conjugated loop. 6 pi electrons does fall into that sequence provided by Huckel's rule, right there. So all 3 checks are met, and this molecule is thus aromatic. In this next compound, we do have a ring, so there is a loop of atoms. But first, I'm going to add in all my lone pairs and implicit hydrogens. The nitrogen has a lone pair, and these 4 carbons each have 1 hydrogen. I'm hinting at it because that last carbon has no double bond, and it has no charge, so it has 2 implicit hydrogens. That makes it sp3 because it has 4 single bonds. We have to be careful in looking out for implicit hydrogens because we can't just assume all the atoms are sp2. This molecule doesn't pass the first check because there is no loop of sp2 atoms. There is no closed loop because there is an sp3 atom in the ring. Thus, this molecule is non-aromatic. And that first molecule was aromatic. What would a similar molecule look like if it was aromatic compared to that second molecule? It would be a similar ring, just with a double bond on that nitrogen. Now, let's go through our checks. It is a closed loop. All atoms are sp2 hybridized. We can draw in our implicit hydrogens just to make sure. So we have our closed loop of conjugated atoms. Now we can assume the molecule is flat because there's nothing telling us otherwise. And so we just have to look for the number of pi electrons that are participating in this conjugated loop. There is a lone pair I see, so let's consider what orbital it's in. That lone pair on the nitrogen can't be in the p orbital because that nitrogen already has a pi bond. It's already connected. So the p orbital is full, so that lone pair is actually going to be in an sp2 orbital. So we don't have to worry about that one when we're counting pi electrons. So we only have to count pi bonds now. We have 1, 2, 3 pi bonds. And again, 3 pi bonds equals 6 pi electrons that are delocalized in the conjugated loop. Again, just like the last example with the benzene ring, 6 pi electrons does satisfy Huckel's rule, so this molecule is indeed aromatic. Now, let's look at the third molecule. I'm going to add in my lone pairs and my implicit hydrogens. We have a closed loop. It is the ring. And all the atoms are sp2, even the oxygen. However, we need to define our closed loop. The closed loop are these 6 carbons. We do not include the oxygen or the double bond that oxygen has with the carbon. This is important because we need to define our closed loop and we do not consider anything outside of the closed loop. We can assume this molecule is flat. And in the closed loop, there are no lone pairs we need to think about. So we simply count our pi bonds. Again, we have 3 pi bonds, meaning 6 pi electrons that are delocalized in this conjugated loop. So it follows Huckel's rule as well, and this molecule is aromatic. It is important that you remember not to consider any atoms or their bonds that are outside of this conjugated loop, because if we did so, we would end up at the wrong answer. If we were to consider that oxygen, then we would say the oxygen also has a pi bond, and that would add 2 more pi electrons to our count that we would say are circulating throughout this conjugated loop. That would put us at 8 pi electrons. And 8 pi electrons doesn't satisfy Huckel's rule. But the first 2 conditions are still satisfied, so if we were to consider the oxygen, we would say that this molecule is anti-aromatic. However, that is not the case because we are not considering the oxygen just for purposes of aromaticity. Determining aromaticity is a skill that builds off of previous topics, so if you are confused on determining the hybridization of atoms or a conjugated system, please check out my previous videos on these topics. Let's look at some more molecules. For this next molecule, we do have our ring, so we do have a loop. Let's add in our lone pairs and our implicit hydrogens. All of these atoms are sp2 hybridized, so it is a conjugated loop. The oxygen is sp2 because it follows the 2 checks for an sp3 atom, or an atom that looks sp3, but is actually sp2. Those 2 checks are it has at least 1 lone pair and it is next to an sp2 hybridized atom. We can draw a resonance structure to prove it. Let's push the lone pair to our bond. And now since that carbon has too much stuff on it, too many electrons, we're going to push that pi bond out onto the next carbon. So our resonance structure is going to look something like this. Now the oxygen has 3 areas of electron density, so it is sp2. Now we can also assume that the first molecule, or the first resonance structure, is flat. So the first 2 checks are satisfied. Now let's determine the number of pi electrons participating in that conjugated loop. We do have to look at the 2 lone pairs of the oxygen. Now when we looked at the resonance structure, only one of those lone pairs contributed to making a pi bond. Thus, only one of the lone pairs on that oxygen is in the p orbital. It doesn't matter which one, it's just the one that we choose. This also makes sense because if an atom is sp2 hybridized, it only has one p orbital. Thus, only one lone pair can be in that atom's p orbital. The other lone pair would reside in the sp2 orbital, or in one of the sp2 orbitals. Since we have one lone pair in a p orbital and 2 other pi bonds, this gives us a total of 6 pi electrons that are delocalized in the conjugated loop. This follows Huckel's rule as we saw in the previous examples, so this is an aromatic molecule. Now the second molecule, we have another loop. It's a ring, but it's more of like a square. Now all the atoms are carbon atoms. Let's add in their implicit hydrogens. They each have 1 implicit hydrogen because they're each connected to a double bond. So they're all sp2 hybridized. The first condition is checked. There are no lone pairs involved. We can assume this molecule is flat because there's nothing telling us otherwise. The second check is involved. Now, we have 2 pi bonds. So 4 pi electrons are delocalized throughout the conjugated loop. This, unfortunately, does not satisfy Huckel's rule, which follows this pattern. Since the first 2 checks were met, but the third was not, this molecule is anti-aromatic. In this third molecule, there is a closed loop. The 2 carbocations are actually sp2. Let's draw in our implicit hydrogens. Since these are carbocations, they only have 1 implicit hydrogen each. That's what gives them their positive formal charge, the fact that they don't have a second. Since all of these atoms involved only have 3 areas of electron density, we have a conjugated loop. Now, we can assume that the molecule is flat. And for our third check, there are no lone pairs, so we only have to consider pi bonds. This molecule, we only have 2 pi bonds, just like the last one, so we have 4 pi electrons that are delocalized throughout this conjugated loop. This does not fit Huckel's rule, just as the last example. So, the first 2 conditions were met, but the third one was not met. This molecule is also anti-aromatic. When looking at this new molecule, there are different conjugated loops that we can make because there are 2 rings present and all of these atoms are in fact sp2. Let's draw in our lone pairs and implicit hydrogens to ensure that. To define our actual conjugated loop, we need to make the largest loop possible, no matter what the loops that we can make within it are. So the largest loop we can make possible involve these atoms. The oxygen and its pi bond are outside of the loop, so we can disregard those when we're looking at aromaticity. Within the conjugated loop, there are no lone pairs, so we only have to look at pi bonds. Within the loop we defined, there are 4 pi bonds. This gives us 8 pi electrons that are delocalized throughout the conjugated loop. That issue comes with Huckel's rule, because Huckel's rule says that we have one of these number of pi electrons in our conjugated loop, and 8 does not fall in there. So this molecule fits the first two conditions, but not the third, so it is anti-aromatic. Just to be clear on what our conjugated loop was, it went around the two rings. This is important because it can be a little confusing since this molecule has a benzene ring in it, which is aromatic. However, we do have to look at the largest loop we can create, regardless if there are smaller loops in it. Thus, this molecule is anti-aromatic. Let's put this all together and look at a nitrogenous base of DNA. The biggest loop of conjugated atoms that we can make, well, first, let's go through our implicit hydrogens and lone pairs. There we go. So, let's look at what atoms are sp2 hybridized and what's the biggest loop that we can form of those sp2 hybridized atoms. Now, the sp2 hybridized atoms are all the atoms here except for the hydrogens, of course. If you want to draw the resonance structures for yourself to prove that, go ahead. But the biggest loop of sp2 hybridized atoms that we can make is this. And specifically, drawing the connection throughout, right there. Now, we can assume the molecule is flat because nothing has told us otherwise, so the first two conditions are met. Now, these two nitrogens don't have a double bond, but they do have a lone pair. Since they are sp2, you can, again, draw the resonance structure to prove this, and do not already have a pi bond. The lone pairs that they have reside in the p orbital. If you were to draw the resonance structure, you would see that those lone pairs can form pi bonds. So we already have two lone pairs that contribute to the number of pi electrons in our conjugated loop. Now, for the two nitrogens that do have a pi bond, 1 and 2, they already do have a pi bond. So the lone pair that they have cannot be in the p orbital because the p orbital is already filled by those two electrons in the pi bond. The lone pair on those nitrogens, respectively, are in one of the sp2 orbitals on that nitrogen. Thus, we don't have to figure or worry about any of the other lone pairs, only the ones on those two nitrogens where the lone pairs are yellow. So we just have to count the rest of the pi bonds now. There are 1, 2, 3. So 2 lone pairs contribute to the pi electrons in the conjugated loop, and so do 3 pi bonds, giving us a total of 10 pi electrons. If we were to look at Huckel's rule, I'm going to write out the sequence again. We see that 10 does fall in there, so all 3 conditions are met, and this molecule is aromatic. Thank you so much for listening.